this webinar. Okay, hello everyone and welcome. Thank you for joining us. My name is Xu Ju. I am with Industrial and System Department at North Carolina State University. And Dr. Speckle, he is with Arbor Uni OHS at Amsterdam. This year, Dr. Speckle and I, we will co-host the MSDTC webinars. For today, we are honored to welcome Dr. Penfield as our distinguished speaker. She is the Vice President of Research and Machine Learning at Velocity EHS, where she has led AI-related initiatives over the past few years. And with more than a decade of experience in developing AI solutions, she brings an exceptional depth of knowledge in applying machine learning to address real-world problems. And before that, she received her PhD degree from electrical engineering of University of British Columbia in Canada. So Dr. Penfield today will give us a presentation talking about how we can utilize or take advantage of AI to enhance workplace safety, particularly in ergonomic solutions. So with that, I will turn it over to Dr. Penfield. So welcome, Dr. Penfield, and thank you for giving us this presentation. Thank you.
Thank you so much for having me. I appreciate it. Hello, everyone. I'm going to give a presentation about 30 to 40 minutes on what I believe is the future of AI in ergonomics assessment software, particularly industrial ergonomics. Let's see. So you already had an introduction about me, and I'm not going to talk a lot more about that. The one thing that I want to emphasize is that I understand this is a very elite group of people and highly specialized in the area of ergonomics. I am not an ergonomist, so what I'm about to share with you today is truly focused on AI or application of AI in your area of expertise. So by no means I claim to be an ergonomics expert, but I'm hoping that the presentation is inspiring for more ideation and brainstorming as to how new AI technologies can enhance work safety in future. So my presentation has two parts. The first half is about the history of AI in ergonomic software and the limitations and challenges that has been around for the past almost 8 years. And the second half is about future innovations and what I think we can expect to see in the next few years. By the way, if anyone has any questions, I'm very comfortable to take them on the spot, so you don't have to wait until the end of the presentation, but if you're more comfortable to do it that way, please do it. Also, I'm not checking the comments frequently, so if you see something in the comments that I need to pay attention to immediately, please voice it. Thank you.
There is a Q&A button at the bottom of this interface, so if you have any questions, please use that Q&A function to ask your question.
Excellent. So let's start. Going with the first half, which is mostly about the history of AI in this context and the limitations and challenges. To the best of my research and knowledge, a company in Ann Arbor, Michigan, called Human Tech, initially started to use AI in the ergonomics assessment software. The idea was instead of, there were a lot of challenges in supporting employers who had a lot of workers who perform repetitive manual tasks with their ergonomic setup and the kind of musculoskeletal injuries that were developed over time from bad postures, performing repetitive tasks. And some of the challenges were they had to dispatch ergonomists all the way to some workshop, factory, manufacturer facility, and they would eyeball the workers and try to come up with some ergonomics assessment and make recommendations in order to prevent those injuries from happening over time. It was a very time-consuming process, sometimes costly, and as you know, it's not like there is a large number of ergonomists around that anybody can go and hire them at any time. There's a relative scarcity in this area of having experts who can support employers. And they were thinking about some sort of a scalable solution that can provide a lot of assistance and bring a lot of value to those workplaces. So they used AI in a manner that somebody could use their phone and take a video of a worker performing a repetitive task. And the point of using AI was to find the location of joints in every frame of that video. Once the joint locations were identified, they could calculate different angles of different joints and apply ergonomic science on top of that. For example, they could define different ranges of angles and see how often they enter those ranges. They could also see the duration as to how long they stay in different ranges of angles. And based on that, come up with a risk assessment to inform the customer that if your worker is going to perform this task repetitively, over time, they're going to have, for example, right shoulder injury or any other kind of injury. So that was back in 2016, 2017, and it had a significant contribution to workers' safety in many different contexts, in industrial contexts particularly. However, there were a lot of challenges with the technology that was used back then and some of the limitations that I'm going to review here. The first one, the first limitation is back then, the kind of computer vision technology that we had in AI community, or we call it machine learning community, it was limited to a two-dimensional perception of the body. As in, if somebody gave me a photo, an image of a person, in 2016, we as in machine learning scientists still didn't have developed the kind of reliable, robust models that could take an image and identify X, Y, and Z, like three-dimensional location of joints in a body. And the fact that we were focused on two-dimensional models back then introduced the problem of inaccuracy. So here, I have the avatar of a made-up human, and I want to calculate the angle of the elbow. If I view it in a 2D point of view, depending on the camera and the positioning of the camera, the elbow can be perceived as almost 40-degree angle. Whereas, like, depending on the reality of the three-dimensional space, the angle could be something completely different. Like in this case, it was actually almost a 90-degree elbow. And that is one of the fundamental problems with a two-dimensional motion capture technology in this context. So if you want to build your risk assessment on top of joints that only have two dimensions to them, X and Y, you are prone to introducing a lot of accuracy in the angles that you calculate. And all the analysis that follows those angles could be impacted by that inaccuracy. So that was one of the limitations and challenges with the technology that existed back then. Moving on to the next limitation, it was body key points. So since then, there's been a lot of development in this space, and there's been more models that are published by different researchers or tech companies for motion capture. There's been also publications of data sets that people could use to train their own model. The most famous one is the 3.6 million data set. Like anybody who Googles that, they can find that data set. It's highly referenced, very, very prominent data set. But the key points that these models or these data sets come with are limited to generic applications that people who developed them had in mind. Because ergonomics is a relatively niche space from the point of view of artificial intelligence scientists. So I live in Seattle, and like most of my friends in this space work for tech companies like Google, Amazon, Meta, and others. And their focus is mainly not on a very particular industry, such as like industrial ergonomics. So if they develop a model that can be used for motion capture, they have other applications in mind. And the key points are not designed for ergonomics applications. So if someone wants to calculate, for example, net rotation angle, they need a number of key points. They need left ear, they need right ear, they need left shoulder, and they need right shoulder. If they have all these 4 key points, then they can create the planes of the head against the shoulders and then say what the rotation is. But if the model doesn't give them all those key points, then it's impossible to calculate the rotation of the angle. So point here is limitation of key points results in limitations of the angles that we can calculate. And that would diminish the comprehensiveness of the risk assessment that we can do on the videos. Shu, can you confirm that you can still hear me?
Yes.
Perfect. So next limitation or a challenge was challenges with mathematical angle definitions. This is an interesting one because sometimes even if you have all the key points to calculate an angle in a 3-dimensional space, in the absence of biomechanical expertise, defining the angle itself in a mathematical way so you can put it in software could be quite challenging. For example, going back to the neck rotation angle, you got to follow quite a few steps to be able to estimate the angle. And this was one of the challenges that has been around to reliably define angles of different body parts before we can apply ergonomic science on top of it. So there has been a need for some studies that can, in a mathematical way, not in a qualitative way, because I've talked to several different professors from different universities, and we ended up working with 2 professors in University of Cincinnati. And one of the challenges that we had is that maybe qualitatively they could describe what an angle would mean, but to put it in mathematical terms was quite challenging itself, especially for more complicated angles. Another limitation that has been around since 2016, 2017 is advanced biomechanical assessment. For example, we never had back compression forces calculated through the software because the software was intended to be easy to use so that it can bring value to a very large number of users. But at the same time, one of the limitations of that was how to come up with a software that is easy to use, but at the same time can do very advanced assessment for you. And that trade-off has not been very favorable for advanced assessment, such as the example that I have here. That's another limitation that has been existed for a very long time. Another limitation is static assessment. So all along, and I would say even up to today, to this day, the kind of AI-powered ergonomics assessment, and in this context, I'm talking about non-wearable ones, so just from a video. One of the challenges is that a video is made of frames, a lot of frames, and the assessment is done on individual frames. So if you take one frame and you identify the joints, their location, the angles, all of that, you're still viewing it from a static point of view, as in the object, the subject is not moving. So some dynamic characteristics of the subject, such as acceleration of the joints, is not used or hasn't been used at all for ergonomics assessment in any context. Even though there has been some research in ergonomics literature that I've seen in using acceleration, and not that that space, as far as I've seen, is like super developed, but we haven't been leveraging anything in that context at all so far, because the analysis has always been from a static point of view. Another limitation was root cause and controls analysis. So something that we've seen a lot in velocity. So Velocity EHS acquired Human Tech, so they basically became part of Velocity EHS family, and they had a very large number of customers. And one of the things that we've seen with the users is sometimes a risk assessment is performed, and I'm going to play a video here, and you're going to see a typical one. So this worker is performing boxes. And I'm going to pause the video right here. So the worker is placing a box down, and they have to bend to do that. And as you can see, the color-coded motion capture for the back shows red, which means there's a risk associated with high risk associated with the back. We had a lot of customers who would see a video like this, a typical video like this, and because they don't have ergonomics expertise, they would attribute high risk to the wrong causes. For example, they think, what's happening here, back here? Sorry about that. They would think the box is too heavy, therefore it's a very risky task. So if we have lighter boxes, then our worker is not going to be injured over time. And because of that attribution, or I guess a false judgment, they would implement controls that are not really bringing the risk down. So the software needed to evolve to assist the customer, not just with the risk assessment, but also help them with root cause identification and controls recommendation. We had to bring it home. Even if you had the most risk assessment, most accurate risk assessment in the world, it's not enough to bring the risk down. And we are doing all of this ultimately to bring the risk down and prevent injuries. So this was a very significant limitation that existed in the software that was initially launched in 2016, 2017. And all the companies who copied Human Tech more or less carried these limitations with them forward. Moving on to, I think, the last one that I have on my list, limitation of hand risk assessment. So hands are very tricky when it comes to AI models compared to the whole body, because if you want to perform any sort of risk assessment associated with hand-heavy tasks or very dexterous tasks, you need a lot of key points. Like for one hand, typically you need 21 key points to be able to capture the movement of the fingers, whereas you can describe the whole body with 20-ish points. So one hand can require more key points than an entire body even. And the models that we had back then weren't very good at capturing the motion of hands. And because of that, the risk associated with different types of grips were not captured in our software or any software back then. Even to this day, the risk assessments that are associated with hands typically are incredibly limited. Typically, everybody stops at wrist. So even if they can capture a key point or two key points in the hand and the palm and in the wrist and elbow, they can calculate the angle of the wrist, but it doesn't tell you much about what your fingers are doing and what kind of risk you might be carrying out by the type of grip. Like if you're holding a tool for a long time with a type of grip that is very, very intense on your body, that kind of risk has not been captured. So that's been another limitation of the existing software in this context. So those are the limitations that has existed. My list was not necessarily exhaustive, but I tried to hit like the big ones, particularly for anybody who might not have prior exposure in this area. The second half of the presentation is what we can anticipate in future to see with respect to these limitations. Given that the AI community or the machine learning community has come a long way since 2016, 2017. One thing that I think we can expect to see is investment in data chambers. So what I mean by that is, if we want to have three-dimensional models instead of two-dimensional models, we need the kind of data that allows us to train three-dimensional models. On top of that, if we want to overcome the key point limitations that I exemplified, for example, neck rotation angle, as the example in the presentation, we need to make sure the data sets provide those key points. So after we train models, the models can infer the location of all the key points required to calculate the angles that are valuable for risk assessment, for ergonomics assessment. And I think probably companies will move into a little more investment into having their own data chambers. We invested in University of Michigan. We partnered with one of the professors in University of Michigan, Professor Sang-Hyun Lee, and we paid for Vicon equipment to build a data chamber in one of their labs. And over time, we had the equipment set up with different subjects of different body size, different genders, different colors, different characteristics, perform a wide variety of tasks that we anticipate to see in industrial setting in order to be able to collect the kind of data that's required to train AI models that can robustly give us three-dimensional motion capture with all the key points that are required for a comprehensive or close to comprehensive ergonomics assessment. So that's one of the things that I think some of the companies will start investing in future, because the publicly available data sets out there are very limited in this sense, given that people who created those data sets didn't have ergonomics application in mind. They had other applications in their requirements. So speaking of three-dimensional motion capture, the machine learning community has come up with new architecture, neural networks architecture, or we call it deep learning architectures, that are very capable in the context of motion capture compared to what we had 2016. Like back then, like I myself couldn't come up with a robust model that can have a three-dimensional motion capture from one device, from one camera. There are some solutions out there that can, for example, take multiple cameras synchronized and based on that, come up with a motion capture. The challenge with using those technologies, like the Stanford method is one of them, is that it proved to be very difficult for our customers to leverage that sort of technology, especially like having more than one recording and having it in a synchronized manner was too much work for a typical user. And it was highly preferred if we could capture the motion of the subject using only one camera and nothing else in a three-dimensional manner. And I'm going to record this video to give you an example as to where we are today in terms of AI technologies and what can be done so here I have a subject who is a grad student in University of Michigan, and he's going to perform some tasks. This is a very simple warm-up video. And on the left, you will see two-dimensional motion capture that is montaged on the body of the person with all the key points. And on the right, we have three-dimensional motion capture, especially the bottom ones are the newest generation. We see V6, V7. These are like version 6, version 7 in the research that has been done. So the bottom ones are the closest to what passed all the requirements and the tests, the quality tests that has been in mind. So as you can see, the subject is performing a work, and this is all from one video. The model can estimate the location of joints in a three-dimensional space. And you're seeing it from two different angles. We are plotting it in two different angles in three-dimensional space. Something I should mention here is one of the limitations that existed in the past in the two-dimensional space was the problem of occlusion. Occlusion means from the point of view of the camera, a part of the body is not visible. Either it is occluded by a tool or it is occluded by their own body, like they have turned around and their body is blocking their left shoulder from the point of view of the camera. And two-dimensional models are very limited in estimating the location of joints when you can't see them in the video. But three-dimensional motion capture can overcome that problem. And even if you can't see somebody's joints, they can have a very reasonable estimate of where the joints are. And I'm going to explain why in a second. And that becomes important when a user has a video in which, for a considerable portion of the video, let's say half of the video, a body part is not fully visible from the point of view of the camera. In two-dimensional world, we can't give an assessment for that joint for like half the video in this example. So your assessment is relatively limited. Whereas if you could have three-dimensional motion capture, then for all of the video, you can have reliable assessment for all of the joints of the body. The reason that three-dimensional models are able to do this is they have a perception of depth, unlike two-dimensional models. So if a two-dimensional model doesn't see a joint because it's blocked by a tool that a worker is holding, or they have turned around and we can't see an arm, the two-dimensional model can't think that, oh, behind this object, there is a joint, because they don't have a perception of depth. Three-dimensional models work very similar, most of them work very similar to human way of perception, in the sense that they look at the previous frames of the video and they look at future frames of the video. And they're like, oh, I saw this joint a few seconds ago and you turned. So I still have an idea where it should be in a three-dimensional space. So a three-dimensional model actually looks at the frame of a large number of frames in future and past to process one given frame. Whereas two-dimensional models only look at that one frame and not the other frames to make an inference. So that's why three-dimensional models are very capable of handling occlusion. Next is mathematical angle definitions. So I think more partnership between industry and academia can be very helpful in this space, to be able to define angles that are not straightforward to come up with, like the neck rotation angles. So it requires a lot of brainstorming and discussions to ultimately come up with a quantitative description, like a mathematical description of the angles, as opposed to just a qualitative description as to what that angle could mean. And I think more publications in this space can be very, very helpful. And we are trying to publish papers in this area to help anyone who wants to develop software that can calculate more complicated angles. Another improvement in future, I think, could be integration to biomechanical assessment. For example, there are applications such as 3D SSPP out there, and they can perform more advanced assessments. In the past, there was no integration to that sort of 3D SSPP when we had AI-powered tools. And 3D SSPP and other tools that I have seen, at least so far, are very difficult to use, in the sense that not only you gotta learn the user interface and all of that, but also if a worker is going to perform a task and they have 40 different postures in 1 minute, you gotta define every single posture in three-dimensional space for all the joints and go to the next posture and next posture, next posture, very time-consuming assessment. And I think in future, we can see more automations and integrations to these advanced assessments. For example, if there is video of a worker, maybe we could come up with the 3-dimensional motion capture. And maybe that motion capture can be fed into an application like 3D SSPP programmatically. So nobody has to use the user interface of 3D SSPP. And then 3D SSPP can come up with the biomechanical assessment that can be used for better ergonomics assessment or better risk assessment. Risk assessment. Of course, 3D SSPP also needs forces as inputs, and maybe initially those could be manual, and maybe in future those could be estimated too. But at least for the joints themselves, I think the 3-dimensional motion capture technology opens the door for the kind of integration that was not possible in the past, and we haven't seen it so far. And that can make even use of applications such as 3D SSP a lot easier. And again, 3D SSP is an example here. There are other applications that do similar assessments. This is just one that I have been more exposed to. But I think we should see more of that in future. Let me check the time. Yeah, I'm good. Acceleration-based risk assessment. So there are very clever ways that we can calculate the velocity and acceleration of joints from a video if you calculate the joint locations. I myself maybe was a little bit naive initially when I thought about this problem, because I thought, well, if I could have the position of a joint, then I can go with first and second derivatives to calculate velocity and acceleration. But that's a very naive point of view, because it's very common for industrial settings that the camera person is moving. So they're recording someone and they're following them. Or they're recording someone, they're moving and capturing them from different angles. As they move, even if the subject is not moving, the location of joints in the picture, in the video, is moving. And if we go with a very naive approach, and say like, oh, I have the position, I'm going to take its derivative to get the velocity and acceleration, it's not going to work, because the movement of the camera can distort all of those calculations. Even for a fixed subject, I can have a camera moving and it creates the perception as if like the joints are moving, even though joints are constant. So we need like more advanced modeling techniques of the whole body in order to be able to calculate velocity and acceleration from joints from a given video. And here you can see an example of measured accelerations against calculated accelerations for a subject. And on the left, you have the 2-dimensional one montaged on the video. In the middle, you have the 3-dimensional depiction. And on the right, you have the calculated and measured acceleration. This is for the lower arm segment of the body. And I think if this information is more available, this kind of calculation can be done, these estimates can be done, then I think that opens the door for leveraging ergonomic sciences on top of that in order to come up with even more accurate or more comprehensive and better risk assessments by using acceleration of joints, which is something that has been absent up to now. We haven't been really leveraging this sort of data for ergonomics assessment. I'm hoping to see more of that in future. Root causes and controls, pretty big deal. And here's a very simple example. There are different ways that I think software can assess users with root cause identification and controls. And very simple way is if the risk of a particular joint is high after the initial risk assessment, then using ergonomic sciences, we can come up with a list of all possible causes that can result in high risk for that particular joint and show them to the customer and let the customer pick them Like here, there's a very simple example, like part storage is too far away. And users, for example, can see a list, a drop-down list, and pick from them. And based on the user's choice of causes, we can also recommend controls that are associated with those causes. And implementing more software in this context can be hugely beneficial to customers because, again, they attribute the high risk to the wrong causes, like a lot. They're not ergonomists. And a more sophisticated way to do this, I think, in future is if we could identify the object, like the tool that somebody's interacting with, or if we could identify the task, like what was it that they were doing that resulted in high risk in right shoulder? Like what was the action itself? Were they pulling a cart, pushing a cart? Were they carrying an object, placing an object, lifting an object, and many other things, reaching out for an object? If we could use AI to identify the action and maybe even the object that they were interacting with, then the root cause nominations can be more to the point as opposed to a very comprehensive list that half of it might be completely irrelevant to that particular task that was performed, and be even more helpful to the customers with the root cause identification and associated controls. But I expect to see more of that in future, more of this sort of support, not just the risk assessment part of it. Last one is hand risk assessment. So here's an example of different categories of grips that someone might be interested in. This is not by any means like an exhaustive list, but let's say somebody wants to start with these 6 different kinds of grips. It is possible to have models, AI models, that can look at a worker performing different tasks, especially tasks that are very heavy on the hands. And here in these pictures, I'm showing you part of the research in this context. The white color that says GT, that's the true answer. Like what is the actual grip that what we knew when a worker was performing a task. And the green is what the AI model could come with and say that, oh, you had a diagonal grip. I can infer from your hand position that this is a diagonal grip. And this can be a relatively difficult task from AI point of view for workspace, because in all these pictures, as you can see, people are wearing gloves, and that's sometimes complicates things from an AI, like machine learning science point of view for ML scientists, especially if the glove is, for example, has a color closer to the background, or if you're wearing a gown that is white. Like we have some videos from some surgeons. We are collaborating with a surgeon facility in California, and if a surgeon is wearing like white covers everywhere and the gloves are also white, like we need more advanced ML models that can still estimate the key points of the hands in order to be able to infer what is the kind of grip that they have. And if the models can do this part, then it opens the door for ergonomics experts to say that, oh, all right, now if I know how long they're having this type of grip or how frequently they go in and out of it, I can estimate the risk in some shape or form and bring more value to users, to be able to bring the risk down over time and, again, prevent injuries in different contexts. In the example of the surgeons, they train them for many, many years, and they're very expensive assets to hospitals and other facilities, and they perform several surgeries every year. I'm sorry, every week, several surgeries. And it's very common to see surgeons injure themselves, like, and have different issues with forearm, for example, or wrists. and they have to perform fewer surgeries at that point, which is a huge loss. That's just an example. There are like many different applications in which are very hand heavy, and trying to reduce risk in those areas are very valuable. I think that's the last one that I have. How did I do on time? 41. There should be enough time for questions. That's overall a presentation of what at least I believe are some of the limitations that exist today in terms of using AI in ergonomics assessment software, and what we can anticipate to see in future to overcome those limitations and challenges. Thank you.
Thank you.
Thank you. All right. So so before we jump to the Q&A session, I think there are a couple of things I think I can echo what Dr. Penfield mentioned in her presentation. So I think back in 2016, at that time I was also involved in a research trying to figure out how to reconstruct human postures from cameras. And like Dr. Penfield mentioned, one camera can only provide 2D information. So a natural solution would be that what if we use two synchronized cameras? So at that time, I think we were working on a solution that we use two cameras placed orthogonal with each other to reconstruct the 3D human posture. But again, it is indeed a problem for safety practitioners to use that system because they don't want to spend time to calibrate the two cameras. Also related to the research discrepancy between computer vision field and ergonomics. So in computer vision, if you look at the reconstructed human pose, you can see that their stick figure looks very simple. So there is a left shoulder, a right shoulder. But in ergonomics, in biomechanics studies, if we are more rigorous about our study, if we look at our anatomical reference books, there's no joint called shoulder joint. So when they say left shoulder, do they mean the glenohumeral joint? Do they mean acromion? We don't know. So that would make some issues when we try to use the ISB standard or ISB recommendation to calculate joint angles. Also related to joint angles, we know that so some of our joint angles are in 3D dimensions, so we need to use other angle decomposition to decompose the rotation matrix in order to get the joint angles. But we know that if when we decompose the joint angles into three other angles, if the second one is very small, then the first one and the third one would be very sensitive. So sometimes we will get a very large angle, but that angle could be artificial. So our joint angle is not that large. We just got an artificial number, large number. So indeed, so when we do research in ergonomics, particularly if we want to bring some new technologies in ergonomic solutions, we are encountering some issues which has been very well organized, summarized by Dr. Penfield's presentation.
Okay. Thanks for that comment. One thing I want to add to that is, I think you have a very good point about, for example, what does right shoulder joint mean? Again, most of the tools that have existed historically, whether data sets that can be used for motion capture or the models that have been published for motion capture, they haven't been developed with ergonomics application and expertise in mind. Typically, like ML scientists have developed them for other reasons. What I think is important to be done, which is what we have done in Velocity, is if you remember, I mentioned two professors in University of Cincinnati. I have to stop sharing screen to remember their name. One of them is Professor Kermit Davis. I can't remember the name of the second one. Was to see when it comes to data sets for AI model training in this context. Vicon equipment, for example, is a very common equipment to collect data. Like you bring a subject to the lab, you install markers all over their body, and they perform a task. And the Vicon cameras can measure the location of all the markers throughout that task. And you use that data to train an AI model to be able to do the same thing in the absence of markers. what we had to do, and this was very time consuming and very challenging, was to determine that if we care about the location of a joint inside body, like internal, obviously we couldn't cut somebody open and put a marker there in their shoulder. We could only put the markers, place them on the surface areas. So the question was, which surface areas are needed to be measured in order to mathematically estimate the location of the internal joint based on that? And these sort of collaborations are time consuming and expensive, but I think they're very important to have meaningful models that can calculate the angles that actually are relevant to ergonomics assessment and has this application in mind, like customized models for this approach. So I think those sort of collaborations are more and more needed between ergonomics experts, whether from academia or from industries, and ML scientists, on the other hand, to ultimately be able to build the models with end use, with ergonomics in mind, and work backwards from there. Like the way it should be done, in my opinion, is first an ergonomist or a collection of ergonomists should decide these are all the angles that we care about. And to calculate all these angles, all these joints are required. Now working backwards from there, we can think about what kind of data set do we need and what kind of AI models do we need to estimate those joints so we can calculate those angles. And that's the path that we took in Velocity for the example of the three-dimensional video that I showed you in the presentation. Back to you.
All right. Yes. So one more thing I want to add is that in the past, when we do traditional occupational biomechanics studies, we put markers on the surface of the body. So there are some certain places, we call them bone marks, and from some old anatomical references, we can tell that, let's say, from abdomen all the way down to the elbow, 15% of this distance will give us the center of the glenohumeral joint. However, nowadays we use computer vision to identify where is the shoulder. But from the computer vision, we know because the algorithm has some issues. The specific identified shoulder joint is slightly moving from frame to frame. So that will result in a moving location of the center of the glenohumeral joint. So we can certainly put a filter to stabilize the location of this joint. But then the next question would be, what would be the cutoff frequency? So if we are so conservative, we will still have that moving noise signals. If we are too drastically apply this filter, then what we got is probably too different from what we really measured. So that is another issue that we are currently encountering.
Absolutely, that's part of the art of the work. Like none of the videos that I showed you today is not filtered. So every motion capture video that I showed you today has gone through a sophisticated filter that is designed specifically for this application in mind and has been reviewed and revised many times by ergonomists and people who are experts in this space to make sure that the filter that is designed with all the poles and all the zeros that comes with it, which I'm sure you're familiar with, are specifically tailored to the kind of industrial applications that we anticipate to see. And the reason that you see such a smooth movement of the subject when it comes to their motion capture is that everything that you see is not just the AI model. There's a post-processing involved. And I didn't go through all of those details because I tried to keep the presentation generic about like the applications here with, as opposed to like very, very AI technical. But I absolutely agree with you that those details are part of the secret sauce to be able to build these models. And I personally am trying to make sure that the work that we've done is going to be published. Like we have submitted a few papers in this space for peer-reviewed publications, because I think everybody can learn from everybody. And if I could inspire somebody from another institution, maybe at some point they will publish their work on top of mine and they will inspire me to do better. And ultimately, it's the worker safety that's going to be elevated at the end of the day. So everybody will benefit from it. It's a win-win situation. So we will have a number of publications coming up in this space, hopefully sometime soon. As you know, peer-reviewed publications take time.
Yeah, we're looking forward to reading those publications. So now let's see what questions do we have in our from our audience. The first question is that how much is the difference in degree between the Vicon system and the video-based analysis? And what is a reasonable estimation for the kinematics for you? So I guess what would be a reasonable error? So there will be error, but what would be a reasonable error between the video-based system and a lab-based motion tracking system?
Yeah, one thing I can do is we have the analysis of the errors per joint, like because for different joints, the error range is different, and we calculate the median of the error. One thing I can do is like we're talking about like very, very small, like few degrees, like 1 degree, 2 degrees, 3 degrees. But what I can do is I can send the table because it's going to be published. Like this is not a secret that I have to hold or anything. I can send the table of the errors to you and you share with all the audience if that works for you. I don't know if this is the kind of arrangement that will work in this context or not. In the past, I have done that. But the errors are deemed reasonable when ergonomics, like when ergonomists decide they are reasonable. As in, we are focused on the endpoint, which is the risk assessment in this context. So even if someone says, hey, my angle is the error is very small, like the percentage of the error is incredibly small, if an ergonomist, or we have a collection of ergonomists that are highly specialized and have been in this space for many, many years, if they determine the angle is still too high for a reasonable ergonomics assessment, then it's too high. So it's completely application driven. And the thresholds that they have determined for me vary for different joints, for different locations of the body. So maybe I'll keep my answer more qualitative in that sense, because if I tell you like, oh, 3 degrees, it's not really going to be probably helping anybody. But I can tell you that it has to be, it has been, and it has to be from the point of view of ergonomists. Like they're the ones who should say if it's accurate enough or not. Given that ultimately the risk scores should be very, very close the absolute majority of the time to what a typical ergonomist would come up with. When we are testing our models, one layer of quality assurance, one of the layers, is that we give the videos, we give 12 videos to a group of ergonomists, 10 ergonomists, well, sometimes 11. And each one of them will come up with their own assessment. And obviously, they're not going to necessarily agree with each other either, because there's a subjectivity, or sometimes they eyeball and like, what was this angle? Like a human can have different perception of an angle. AI models are more consistent in that sense. We take all of those assessments from ergonomists and build a benchmark, as in like, this is the range of what ergonomists come up with for different joints, for example. And we test our AI models against that benchmark to ultimately determine, can this AI model, in the context of industrial ergonomics, perform on par with a typical ergonomist? As in, are the accuracy of the risk assessment within the range of what typical ergonomists will come up with or not? So that's part of the process to be able to determine the values. If you really care about to know the numbers, like the values of the errors, I can stop sharing. As we're talking, I'll pull up the paper and I'll show you that table. If it's valuable, just let me know. I can do it live on the meeting.
That would be very good, because this question was from Tua van der Haven from the Human Movement Biomechanics Research Group from the University in Leuven, Belgium. And I think it would be very interesting to start maybe a collaboration, or at least share your data.
Let's continue as I am searching for the latest version of the paper, and then I'll share a screen again.
Yeah, I can add something here. So I remember that in the past I've read a reference paper saying that a 5-degree difference would be considered as clinically significant. So whenever my students, they work on computer vision based human pose construction, so when they need to discuss whether the algorithm works well or not, I typically just ask them to refer to this reference, whether it is less than 5-degree or greater than 5-degree. However, this is just only for publication purpose, but if we're really talking about ergonomics application, so sometimes if you look at Rula or Reba, they use like 20-degree, 25-degree as a criterion. So if you have this error, and because of this error, you move your identified risk from one category to another category, then even if it's a small error, that would be a problem. So again, like Dr. Penfield mentioned, so there are different perspectives on this. So on one hand, people can say that I want to be accurate. I want to be accurate as much as possible. I want to be as accurate as a motion tracking system. But other people say that we are not trying to beat a motion tracking system. We're trying to just beat the other human ergonomists. As long as my algorithm works as good as other human ergonomists, then that means our system could replace some human work, could make the whole process more automated. So there are different perspectives on this issue, I guess.
There are also two questions in the Q&A section from Wijnand Trom. The first one is the program an online platform or a standalone program?
It's an online platform in the sense that a customer will go to the website and they will upload. Obviously, they use their credential to log in. They will upload their video and fill in the fields associated, like the description of the video and a few other questions that they're asked. And then they ask for the assessment and go. Depending on the length of the video, typically it takes 3, 4, 5 minutes, unless you have a very long video for the assessment to be completed. No humans are involved. Like we have a very, very large number of customers. So like this has to be completely automated. And then maybe I don't know if your audience would care about this, but there's also like some compliance issues, like the face of the person should be blocked when we process the video and all of that. So all of that, those are done. And then the user can see all the assessments, the results, the risk scores, the processed video, as in like the motion. This is part of the QA, as in like visually, you can take a guess, did the AI model did a good job or does it look really bad? Because we show them the processed video with the motion capture montage on the body for 2D and the 3D skeleton next to it. So even a non-AI expert can take a glance and say, like, hey, this looks reasonable to me. So all of that is online and without involvement of any humans.
Okay, there's two follow-up questions, and you touched one of the areas. And the question is, how is non-disclosure / privacy for company and workers secured? So one is by blurring the face, I understand.
There are a few considerations. So we had to consult, depending on the region that we are operating in, like US versus Canada versus Europe. Like Europe has GDPR and like has like very different compliance levels. We have different guidelines. As I said, one of them, for example, is we have to delete the original video that is uploaded in a way that cannot be retrieved. And then the process video has to remove the face. So the face is completely blocked with a big circle, a black circle. So there are some considerations as such in order to make sure that we are compliant with the requirements in this context. This goes into a little bit more of a lawyer talk and compliance officer talk, but those conversations have already taken place to protect the privacy of or the identity of the user to the extent that has deemed required by us.
Okay. And Wijnand has one last question, and it's, can you give some pricing info for use of the program? Can you give an indication?
Sorry, could you repeat that? I'm still
Can you-
looking at the last
Can you
version
give
of the
some
paper.
pricing info for the use of the program?
I actually shouldn't comment on that. So the best place to start is to go to ehs.com.
Yeah.
If somebody really wants to use it. Maybe I want to add something there. Yes, if someone to use it as a customer, like ehs.com, and then industrial ergonomics is the best way to start. If someone is in an institution that does research, I am very open to partnership. So I have partnered with a professor in University of Toronto, Dae-Ho Kim, a professor in Rutgers University, Main Liu, a professor in University of Michigan, Sang-Hyun Lee. We pay for the grant research of three PhD students who have done research for me in this context to allow me to move on faster. The data chamber that you saw, for example, that I showed in the presentation, is built by a PhD candidate in University of Michigan. We have worked with two professors in University of Cincinnati that I mentioned. I am very pro collaboration for research. So if you're asking in that context, please reach out to me and we can talk to see what we can do together. If you are asking as like a regular user, that like you have workers that you want to assess anything, the best place is to start, or I can link you to a particular salesperson if you want. I don't even know who would be the best person, but I'm sure I can find them. But the best place to start is to request a demo through the ehs.com website, which is our website. Okay, I'm going to share a screen and put the errors on the screen very quickly for the answer, for the question that was asked earlier. I'm going to remove the confusing parts. It doesn't matter. I'm not going to remove anything. It is going to be a little confusing, but that's okay. Share. Where is my share button? Here. Okay. So here, this is a table of errors. These are the median of errors because each video in the test data set comes in many frames, and each frame has its own associated angle. So we're talking about like a super large number of angles. Typically consider 20 frames per second. So your video is 2 minutes long, let's say 100 seconds long times 20. That's the number of frames, which means the number of angles. And then that's for one video. And we have multiple videos in the test data set. So these are the medians of the errors. And there's simple model and more complex model. I don't want to go into details as to what that means, but here are different joints. And initially, they were calculated in this manner to be compared against a benchmark that we had in mind, and that benchmark only published the angles for these body parts. But these are sample examples of the errors depending on the model that we want to put in production. Does that answer your question?
Yeah, Arvin, you're muted.
I am muted.
I'm sorry. I'm just reading other people's question, but I think it did answer my question. So, and hopefully Tours as well. And otherwise, he can reach out.
I know we are over time, but I think I can. If there are more questions, I can stay a few minutes longer.
Okay, is there any additional questions that people want to ask? You can use either the chat function or the Q&A function to ask.
Well, Tur replied that yes, thank you for sharing. So it helped. Thank you very much.
Can you stop me from sharing my? Oh, okay, I can share it here. I stop it. All right, I see. Great.
Okay, so I guess we are a little bit over time right now. If there's no more additional questions, we would like to thank Dr. Penfield again for today's excellent presentation. And also feel free to contact Dr. Penfield if you have any follow-up question. Thank you very much, Dr. Penfield.
Of course, my pleasure. Thanks for having me. Have a great day, everyone.
Bye-bye.
Yeah, have a